Okay. What we're going to do today is we're going to do, turn off my camera for now. We're going to do a proportional integral and derivative example from the Florida Atlantic University. If you're in the class currently, cool, but it's the same exact example as he did in class. So I'm going to pull up the PowerPoint here, and it's going to be this example right here. So I'm going to snip this problem. So let's call this PID exercise number 1. All right. And I'm going to, nope, wrong guy. Let's copy that and drop that in. Bam. Let's make it a little smaller. It's kind of big. All right. A little smaller. Here we go. Set as background. Okay, so let's start off with the problem. So the first thing to do is I always start any problem with givens / assumptions. Givens / assumptions. I do this because whenever you're doing a science, physics, or engineering problem, the problems are going to give you stuff that you absolutely need. And then a lot of the time you're going to have to make assumptions and pull stuff out of your mind, out of your mind that are concepts and ideas and formulas that are expected of you that you should know. So that's why I do that. It reminds me to read through the problem, find what's given, and then to think about the problem and then make any necessary assumptions along the way. So, starting off, the problem. Consider a proportional control of the following first-order system. Okay, so it says, hey, it's a first-order system. Okay. The controlled variable is rotational speed, capital omega, and the control signal is torque T, which consists of an actuator torque and a disturbance torque. Alrighty. The task. Now, when it comes to task or anything that's asking for you to find something, I just call it finds. So the first thing it's going to ask is, it says determine the smallest value of Kp. Okay, so I call that A. So it's the smallest value of Kp, which Kp is your proportional part of your PID controller. So it's asking for the proportional variable. Requires so that the steady state command error will be no greater than 0.05 radians per second. So in this case, and I'm going to abbreviate, so the steady state command error, it says will be no greater, so will not be greater. So we don't want it greater. So it'll be less than or equal to 0.05. And that'll be obviously radians per second. If the desired speed is, so if the desired speed, and I guess I'll put this into the traditional, yeah, I'll do, just for now, I'll put in the traditional omega, which is your radial velocity, which will be 1 radian per second. All right, now B, the second finds. Evaluate the time constant. Well, that's easy. It wants the time constant, which is which is tau. What is tau? And then it's asking evaluate the steady state disturbance error for a unit step disturbance. So C. So we're looking for steady state disturbance error equals question mark for a unit step disturbance. So just to let you know, whenever these problems mention unit step, and by the way, they didn't mention it for the first one, but the steady state command error and the steady state disturbance error are both involved with unit step disturbances or unit step functions rather. Not disturbances, because your steady state disturbance error is your disturbance and your steady state command error is your controller. So we have that. And we're saying, yeah. So there we go. Those are our finds. So the next thing we need to do in the first part of doing this problem is finding the closed loop transfer function. So the first thing I'm going to do, I am going to pull up the PowerPoint again. I'm only going to snip the block diagram. And we are going to do both ways. We are going to do what I call the hard way of finding your closed loop transfer function and an easier way. But honestly, I prefer the hard way because you kind of just see how everything is connected and how everything correlates to each other. So we're going to do that. So let me click on this. So that's pretty big. Let's make it smaller. Okay. So I'm going to write right here, finding closed loop transfer function. Closed loop transfer function. Let me lock this puppy in the background. So the first thing we're going to do, and I'm going to do this just because these capital omegas, I don't like them and I'm not going to write them. So what I'm going to do, I'm just going to scratch them out and give them different names because I just don't feel like writing capital omegas. I just don't. So I'm going to call this capital Y of S. And this is going to be capital Y sub R of S. That's what that is now. So the first thing we're going to think about, we're going to look at each part of the block diagram and figure out what each part it means in terms of a mathematical expression. So first we're going to look at the error portion. And for those of you that are following along in systems and controls or even electrical systems at your university, these are pretty simple. You have a summing junction here, and that summing junction will basically it's like the junction rule from electrical systems. So you have your error function, which is your capital Y sub R of S minus capital Y of S. Okay, so there's that. Done. Next guy we're going to consider is T of S. Now, T of S is going to equal capital E of S times KP. And because you guys know, basically that's just a product. E of S running in the KP, it's a product. Now, the next thing is going to be Y of S. What is Y of S? So Y of S, like all the other ones, it'll also be a product. But a good question is, and not naming this area here some variable, let's just think about what is this piece here? Well, this piece right here is just capital T of S minus T sub D of S. So when we have this, it's simply just T of S minus T sub D of S all over 5S plus 2. So there we have 3 equations, and the goal is we want the closed loop transfer function. What is the closed loop transfer function? Ask yourself that. Well, we know that is your output over your input. And in this case, that will just be Y of S over Y sub R of S. So let's carry on. And let me kind of block this out. I'm not mixing up numbers. I do that sometimes. First thing I'm going to do is I'm going to back substitute the error equation into the T of S. So we have T of S, and I'm going to distribute that KP right away. So it'll be, we have capital Y sub R of S times KP minus capital Y of S times KP. Now I'm going to back substitute that into the capital Y of S equation. Capital Y of S, it's kind of ugly. Capital Y of S. And we're going to have capital Y sub R of S, KP, minus capital Y of S, KP, minus TD of S. And obviously this is all going to be over (5s plus 2). Now, knowing, you know, stuff from way back when, from algebra, intermediate algebra, the numerator is just, you know, the terms are either positive or negative, and they're in a addition or subtraction type of pattern. But we know we can break that up, giving every piece the same denominator. So let's do that. Let's rewrite this and give every piece the same denominator. So we'll have capital Y of R of S, KP, 5 S plus 2 minus Y of S, KP, 5S plus 2 minus TD of S, 5S plus 2. So the next thing we're going to do, because and by the way, let's stop right here for a moment. This is a good nugget right here, this entire piece, because this is everything in the block diagram. Everything we're considering. You have your disturbance, you have your proportional controller in there, and then you also have your output and your input. The things that we are ultimately desiring is all present in this piece. So this is a good piece to have. It's not the end piece, though. Now, because part A, we are concerned with getting our capital Y of S all over Y sub R of S, getting that closed loop transfer function. We're going to assume that the disturbance is 0, and I'm going to write that down right now and show you. So capital Y of S, could just copy, but who cares? Y of S plus 2 minus Y of S, KP, Y of S plus 2 minus T sub D of S, 5S plus 2. Now, because we said that T sub D of S is 0, because we're not considering it in the situation we're in the part A of the problem, when we're concerned with the steady state control error. The input and output of the system all deal with the control. So we're just going to get rid of the disturbance. Bam. We're saying it's 0. Awesome. Beautiful. So I'm going to do the smart thing now. Copy this, because I like to show everything in as much detail as possible. It's just a preference of mine. So let's paste that up. Bam. So now we have that. And I'm going to show an arrow. That'll work. Red will work. So I'm going to rearrange. We're going to find the closed loop. Okay. Now I can group my terms together. Just trying to see how much room I have. So let's pull this puppy up a little bit. Which one do I have? Yeah, I'm going to copy. Actually, I'm just going to move this all over. Trying to be tidy. It's really easy to get lost in the sauce when you're doing all these equations and math. Okay. I guess in that case I can keep flowing, actually. So let's keep flowing. So bam. Back to my unnecessary level of detail. We can take out the Y of S on the left side from both terms. We take out the Y of S, and that leaves that inside term with 1 plus KP 5S plus 2 equal Y sub R of S KP all over 5S plus 2. Mind you, this is we're still on the road of getting the closed loop for the steady state command error. That's where we're heading. So now what I'm going to do is I'm kind of going to come over here and come to the far left, and I'm gonna write the closed loop. So we have y of s all over y sub r of s equal kp all over 5s plus 2 1 plus kp 5s plus 2. I'm going to move this over to the left, and we're going to simplify this a little further. And that's what a lot of these classes come down to. Like, you need to know your calculus, your ordinary differential equations, and you're really coming back to a lot of intermediate algebra. So, you know, the top surface is all the complex, hard stuff that you've been doing in college, but then the meat and potatoes is all the intermediate algebra and then the college algebra. So what I'm going to do here, another color, I'm going to have this right here. We're going to have 5s plus 2, 5s plus 2, and you know, with this guy, mark it out, but it's really can be 5s plus 2 all over 5s plus 2, which is 1. Because, you know, 1 over 1 equals 1. And then, you know, infinity over infinity equals 1. Illustrating that the same thing over the same thing is 1. So knowing that, that goes away. And that goes away mostly. And then last but not least, the thing we've been waiting for is this. Y of s, y sub r of s is going to equal kp 5s plus 2 plus kp. And this is the form that is desirable for part 1, part A. Okay. So that's something we need. So finding the closed loop transfer function was the first thing that we needed to do. Okay. So going down a little further, we can finally start with part A. Part A, finding kp. Now, because it said to find kp when the steady state command error is less than, or in their words, it will be no greater than, which is less than, because it says no greater, less than, just confusing words. Well, and they're saying when the steady state command error. What or how do we find the steady state command error? Well, to find that, we're going to have to use the final value theorem. Now, just to make a point, we found the closed loop transfer function. And if you notice, once the transfer function is found, we see that it is a first order system with only one pole. And you may be thinking, like, one pole, what do you mean? Well, if we just called kp, let's say 1, all right, so it's going to be 5s plus 3. And we've set the denominator to 0. That's when that becomes undefined, whatever that, fraction is. It becomes undefined at that 0. But for this problem, whatever that s is, that is where the pole location is. In this case, it's a first order. That s has no exponent besides 1. So there's there's only one solution to the problem, and so you make it equal to 0, you figure out what your 0 is, and you find out, hey, it's only on the real axis. And I'll show you in a moment. I'll show you in a moment when we do some more stuff. So we're going to consider the final value theorem. So finding KP and yes. So first thing we're going to do is recall that our error function is just y sub r of s minus capital Y of s. And then, and by the way, I did forget to do the second thing, but actually, I'll just do it now. I know I'm being wishy-washy. But if anyone actually watches this, well, perhaps you're desperate. I'm not a professional. It's okay, though. Seriously, I am here to help. Okay. So, and I'm going to make a line. The other way you could find this, and probably a lot of you would already know, if you're taking your standard electrical systems 1 course or some other course, I'm going to denote that h sub c of s, which is your transfer function for your steady state command error situation. We know it's just going to be c of s, which is your controller, h of s, which is your plant, then 1 plus c of s, h of s, which kind of looks like one of your loop rules. And I'm not too savvy at that. I usually stick to the more, knuckle dragger method of doing this stuff, because the more I have to do shortcuts in my mind, the more likely I'm going to mess up. So I tend to do everything more of the hard way. But this looks like I want to say it's a loop rule. Pretty confident that it is. I'm pulling it up right now. I'm taking notes on it. Yeah, in this case, that really comes from a negative feedback. It's a negative feedback rule, which a way to think about the negative feedback rule, and I'm not very good at this, is forward 1 plus loop. And I don't really think I can convey that to you, but if you look on YouTube videos and other places, they will show you. So carrying on. And this particular problem kind of only pertains to the situation that we're involved in. If it's more complex, like, you would have to do a lot more simplifications of the block diagram. So there's that. And we know that C of S is equal to KP. We know that H of S is just going to be 1 over 5s plus 2. That's some things that we know for certain. Okay. So all I'm going to do is back substitute these values into this formula, basically. So C of S is just going to be Kp 5s plus 2, 1 plus Kp 5s plus 2. Doesn't this look familiar? You see? Same thing. So you already know what the final outcome will be because we simplified it earlier. But it'll just be Kp all over 5s plus 2 plus Kp. So that's just to show you another way. When I highlight stuff in yellow, it's usually pertinent information to the problem or just pertinent formulas. So this is a pretty good formula to stick to. Not the end all be all, but it's pretty good. So I'm going to bring this back up, and we're going to finish part A. All these parts. All right, and let's. All right. So we recalled the error function. And another thing that we need to know is that h sub c of s is equivalent to capital Y of s and capital Y sub r of s. And then we already know that it's Kp, and then it's going to be 5s plus 2 plus Kp. We already knew that, but as just to, I'll put it all in one spot to see that it's equivocal to a lot of different things. So the question is, so recalling, we're going to recall the final value theorem. So recall final value theorem. It's simply just this, and I'm only writing the left side just because the professor kind of does that. I really don't like it, but so as the e of t function, so t is not put in here, but as it approaches infinity, the limit as s approaches 0 of s capital E of s. Well, yeah, that's the expression, that's the theorem. So e as that approaches infinity is equivalent to the limit as s approaches 0 of s capital E of s. So we're concerned with the command error, and we want this guy to go into E of s equation. You want that. How do we do that? Okay. So this is kind of an important thing to know. So for the error function, we can just do a little mathematical trick. And the mathematical trick is 1. Good old 1. So what we're going to do for this second portion right here that I'm writing right now, capital Y of S, I'm going to multiply that by 1. But that 1 will just be capital Y of R of S all over capital Y of R of S. And we're going to rearrange that into capital Y sub R of S. And I'm going to we want this to match this. You see what I did there to illustrate? So, you know, things that are a product, you can just kind of move them around willy-nilly. It's kosher. It's allowed. And just to drive that home real quick, it's kind of like saying that we have A and then we have B over B. Well, we can do it like this. It's A, B times B. That's fine. Or it's going to be AB over B. So any of those combinations, they're all the same. So that's what I'm going to do now. And so doing that, I get now H sub C of S times Y sub R of S, which then will now give me 1. Y, capital Y, R of S, 1 minus H sub C of S. Cool. That is now my transfer function. And plugging in what we already know about H sub C of S and Y sub R of S, we can make it look even, nicer. H of S will equal. Now, what is Y sub R of S? It didn't tell us in the first part, but we're assuming, this is the assumption coming out, we're assuming that all the steady state errors involve a step response. That's the assumption we're making, and that's what we're sticking to. I can't really explain why we're making this assumption, besides the fact that the disturbance, we're assuming that's a step response. So because we're assuming that's a step response, we're not assuming, we know. So from knowing that, we're going to assume that the control is also a step response. So 1 over S. And then we're going to plug in 1 minus Kp 5S plus 2 plus Kp. Making this look a little nicer. Not a little nicer, but we're just doing some mathematical magic. We're going to have 5S plus 2 plus Kp minus Kp all over 5S plus 2 plus Kp. We see that these Kp's, they cancel out. Bye-bye. And the final thing that we're going to put in this final value theorem is this. E of S is 1 over S times 5S plus 2 all over 5S plus 2 plus Kp. Okay. So we're now going to plug that into our final value theorem. So we're going to have E as that approaches infinity, the limit as S approaches 0, S. Then we're going to have 1 over S, 5S plus 2, 5s plus 2 plus kp. And then we see here, conveniently enough, that these cancel out. Sweet. So that's why we're assuming step responses. It makes some things easier for us. And whenever you take your limit, whatever this variable is approaching, you're just going to plug in zeros. Well, for this case, if we were approaching 2, you plug in 2. So 0, which is going to leave us with 2 plus kp. This expression is our steady state command error. So since we do not want this to be greater than 0.05, we're basically just going to do an inequality. So we're going to set up the inequality. Which is going to look something like this. And then we're going to have 2 all over 2 plus kp, 0.05. Now I'm just going to do it the way I would do it. I would have 2, and I would distribute the 0.05, because that's something I would just, I would just kind of organically do it that way. Professor does it a different way, but I'm not him. So I'm using my calculator. This turns out to be 0.1 plus 0.05 kp. So I'm going to subtract that 0.1 to the other side. And for those of you who need the visual, I'll just do it all out. 2 minus 0.1 1.9, 0.05 kp, and then we're going to have 1.9 all over 0.05 less than or equal to kp. And then that'll give us 38. 38 less than or equal to kp. Or the other way is be kp greater than or equal to 38. But because we want it to be less than 0.05, and we're saying that kp has to be greater than or equal to 38, we kind of just don't want to mess with that value. So we're going to stick to just 38. So for part A, kp equals 38. Now, the professor talks about units and tracking your units, which I haven't done at all. But if you did and went back and tracked all your units, this would be Newton meters per radian per second. So he said he won't take off credit. But I guess it's important to pay attention to what's happening as you do your math. Taking my time. I really shouldn't be. Beautiful. Okay, so what's the next portion? The next portion is telling us what is the time constant. Well, how do we find the time constant? Well, the time constant let's think about this. Okay. So now we're going to think about the time constant. How much room do I have? Beautiful. So we're finding tau, and we know that the transfer function for the command error situation, that is, where we're ignoring the disturbance, the input disturbance, is this. Kp all over 5s plus 2 plus Kp. All right. Now, let's recall standard form for an equation of motion. If you've taken vibrations or have, taken that level of physics where your standard form or standard, it's just the standard form for a second order differential equation involves mass, dampening, viscous dampening, and your stiffness parameters. Is this? It's going to be m x double dot plus c x dot plus kx equals 0. And so we want this setup. Now this is the first order. So, it's we don't have a whole lot going on. So we're just gonna do some rearranging to get as close to that as we can. So the thing I'm gonna do is I'm gonna pull out that 5. And I'm gonna show you in as much detail as possible. So we pull out the 5. Actually, let me do this because I know some people are forgetful with their math, which is fine. We multiply everything by 5 over 5, right? Or 1. And you can do that. It's kosher. You can multiply anything at any time by 1. So 5 over 5, 2 plus 5 over 5, Kp. So now what I'm going to do is I'm going to pull a 5 out and shove it in the numerator. You can do that. I know, it's uncomfortable. So we're going to have s plus 2/5 plus Kp over 5. And then now this will just turn into So doing a little bit more work. S plus 2 plus Kp over 5. That's as nice as it's going to look. So we can go ahead and solve for that pole if we wanted to. Obviously, we know what Kp really is. So finding the pole, and finding the pole is just finding where that thing is 0, where that denominator is undefined. So finding the pole, we're going to get 5 S plus 2 plus 38 equals 0. Notice I plugged in what we found for Kp. So that's going to be 5s plus 40 equals 0. Cool. And then we're going to have 5s equal negative 40. And then it's going to be your pole is that s equals negative 8. You see how I did that? So it's going to be negative 40 over 5, which yields negative 8. So drawing a picture, here it is. We're saying that this is the imaginary axis. This is the real axis. And because this is a real value, we're going to say that the pole's here. Negative 8, comma 0. So it's stable. This side of the thing is stable. And this side is unstable. So it's stable, and that's the real part of the pole. So, and another way to think of this is we have, if we were going to do the inverse Laplace, well, what would be the inverse Laplace? It would be e to that negative pole times s. So it would look something like this. It'd be e raised to the negative 8s. And we know that the time constant, well, at least I know, I don't know if you know, is 1 over sigma, and sigma being the distance, well, it's the adjacent part of the triangle, or the distance away from the origin if it is all on the real axis. And in this case, that distance is 8, which means our time constant is simply just 1 over 8, or, yeah, it's 1 over 8. Hey, baby. My wife just walked in. I'm live streaming. I know. All right, so that's 1/8, and that unit is in seconds. Now the last part of the problem is talking about the disturbance, the steady state disturbance. And we're going to go back and refer to that really handy part of that transfer function that kind of gives us everything. Right here. Kind of gives us everything we need. Because I don't really trust the arithmetic of trying to do all those tricks with a block diagram. It just doesn't, I just don't like doing it, honestly. Okay. So, copying this down. So in this case, we have the expression that shows us everything. And in this case, because we're only concerned with the disturbance and not the original input goes away entirely. So it's 0. And we can now rearrange to get it, that new transfer function. And by the way, we're trying to find this, which is going to be y of s all over capital sub T b of s equals question mark. So I'm going to rearrange, and we're going to get this disturbance transfer function. So y of s, hold on, okay, plus, because I do everything in the hard way. I don't do it the easy way. 5s plus 2 equals negative t sub d of s, 5s plus 2. And then I'm going to group that y of s out. It gives me 1 plus kp 5s plus 2 minus t sub d of s all over 5s plus 2. Now I can multiply td to the left side and then 1 plus kp all over 5s plus 2 to the other side, which gives me y of s t sub d of s going to equal negative 1 all over 5s plus 2 all over 1 plus kp 5s plus 2. You notice that the difference here is we're missing kp in the numerator, and it's negative. Doing the tricks in class, I wouldn't have just naturally figured that out. I just wouldn't have. So that's why I always like doing things the hard way, because you're typically not going to miss the details. So multiplying top and bottom by 5s plus 2 showed you that trick earlier. T sub d of s will now equal negative 1 5s plus 2 plus kp. We need this. So it's highlighted in yellow. Now, the next thing that we need is to recall the error function. E sub s equal y sub r of s negative y of s. In this case, we don't care about the input. We said it's 0, so it's staying 0. Bam, 0. So in this case, we're going to have to do what we did last time. The v of s minus y of s. Well, negative y of s times 1, which is just going to be times capital T sub d over s, T sub d over s. We have this. We have this. So now, that e of s equal negative and by the way, we're considering this to be h sub d of s. This just for another variable to name the transfer function. Something negative h sub d of s times t sub d of s. And mind you, we consider that capital T sub d of s is step input, which is 1 over s. And so let's plug in what we know. Negative minus 1, 5s plus 2 plus kp times 1 over s. You notice these negatives cancel out. It's really nice. So now let's take the final value theorem, E as it approaches infinity, for the disturbance. Is going to equal the limit as s approaches 0, and we have s 1 over s 1 over 5s plus 2 plus kp. So the s's cancel out, and we're going to plug in zeros for s, and we're going to substitute 38 for kp. So what our outcome turns into which is our answer, is 1 over 40. 1 over 40. And that is the answer for that part of the problem. That is the end of the problem. All parts have been answered. Let's go back and view this at 100%. So there's quite a bit of work involved. We found KP when the steady-state control error was less than or equal to 0.05 radians per second. We found the time constant, and we found the steady-state disturbance error. So it's coming down to really knowing these terms and working the problems. All right, so yeah, that is done with this example.